Recorded today. Good morning, good afternoon, good evening. Welcome to the ZG Earth Data webinar. Today is our great pleasure to have Dr. Michelle Muth speaking about the topic of the influence of sulfur on magmatic evolution. So Michelle got her PhD at University of Oregon, and then she's still working on her postdoctoral fellowship at the Smithsonian before she started her position assistant professor at the University of Washington very soon. And so that we are going to hear the story from Michelle about the oxygen precocity, I suppose. And normally our webinar goes for about 40-45 minutes, but it's flexible because it's a webinar version. And after that, we have about 15 minutes of interaction with our participants. So with that, Michelle, please.
Okay, sounds great. Yeah, thanks a lot for the introduction and for the invitation to speak. It's a pleasure to be here and share some of the information that's been really fun and exciting project to work on. So what I want to talk about for the next hour or so is how sulfur influences magmatic evolution, including oxygen precocity, and also how it relates to the broader scale of volatile cycling in our Earth. So before I jump into the details, I'll just start by thinking a little bit about the big picture and how my work fits into that. So I always found this particular image very striking. This was actually taken from the International Space Station during eruption in the Kuril Islands a few years ago. And obviously it's extremely visually striking, but I also really like this picture because it shows really clearly the close connection that volcanoes have to Earth's atmosphere. And that connection is really fascinating to think about, particularly when we think about the other side of volcanoes, that they're directly connected to Earth's mantle. And so to show this in kind of a visual sense, I'm showing here a really gorgeous outcrop of mantle xenoliths, prototype xenoliths, those green clasts in that gray lava flow matrix. And so we know from field evidence like this that the roots of many volcanoes are directly within Earth's mantle. And so when we think about volcanoes in this kind of broad scale, we arrive at a very kind of zoomed out picture of volcanoes and how they fit into the overall dynamics of our planet. And one of the grand challenges in igneous petrology and geochemistry is trying to figure out how volcanoes conduct mass transfer and mass exchange between Earth's interior and the surface of our planet. And when we think about these kinds of processes, we can set out kind of broad baseline comparisons to start thinking about. So on our planet, we have mid-ocean basalts. We can kind of think of this as our kind of baseline style of volcanism. This is a type of volcanism that occurs on our planet, but also other planets. And even though we're still learning a lot and there's a lot more to learn, we can think of them as relatively simple, well understood systems relative to the other case I'm going to talk about. And so this case is the volcanic arcs. So this is a feature that, as far as we know, is unique to our planet. It's deeply tied to the creation of Earth's continents. And it's kind of a test case, a wildcard scenario compared to mid-ocean ridge basalts because we have the involvement of subducted material. And so we know, even just by looking at the broad morphology of each of these volcano types, that there are some clear differences. So I'm showing here a beautiful picture of pillow basalts. We know that mid-ocean ridge basalts dominantly erupt in this behavior, this very steady, diffuse style of volcanism that results in these really interesting pillows. And in contrast, we know that volcanic arcs are often typified by large explosive eruptions. And so in the United States, many of us witnessed this firsthand by the eruption of Mount St. Helens in the 1980s. But we know that globally, volcanic arcs often have these explosive types of eruptions. And we've made a lot of progress in understanding how explosive eruption style is tied to the process of subduction and the recycling of water through Earth's mantle and into Earth's crust. And so even though we've made an incredible amount of progress in understanding the distinctions between these two geodynamic settings and the types of volcanism that occur in each, there's still some pretty fundamental outstanding questions. One of these questions is how the oxidation state of each of these different settings differs and why that is. So there has been an observation that's been made for a long time now that arc volcanic rocks are commonly more oxidized than mid-ocean ridge basalts. And so I'm showing here an image from one of the earliest papers to look at this closely from the perspective of volcanic arc rocks. You can see that in this compilation, it covers both mid-ocean ridge basalts, that's the oceanic basalts category, and a variety of volcanic arc basalts and andesites. On the x-axis of this plot is the oxidation state of these rocks expressed as oxygen fugacity. If you haven't thought about oxygen fugacity in a while, all that you really need to know for this talk is that higher values of this delta NNO parameter means that the system is more oxidized, whereas lower values means that the system is more reduced. And so when we look at this plot, this histogram, we see that there's a clear offset of arc magmas towards more oxidizing conditions. And this observation has been made over and over again in a variety of settings. And so although this observation has been around for a long time, as I mentioned, there's still some uncertainty as to what causes this offset. And we can think about this in kind of two end-member scenarios. One is that this offset is driven primarily by processes that occur in Earth's crust. So these are processes like crystallization, degassing, crystal assimilation. And in this kind of end-member scenario, we can envision a process where arc magmas don't start out more oxidized than Moore at the beginning of their lifetime, but evolve towards these more oxidizing conditions over the course of crustal storage, crystallization, and assimilation. The second kind of end-member conceptual model is to think about the downgoing slab and how slab dehydration might impact the oxidation state of erupted arc magmas. And so in this scenario, as we all learn, the oceanic plates ducts beneath volcanic arcs, it starts to dehydrate and release hydrated slab-derived materials into the overlying mantle wedge. Well, in this conceptual model, those slab-derived materials would be oxidizing enough that they oxidize the mantle wedge and therefore the melts that form within that mantle wedge. And so it's really this second conceptual model that I'm going to focus on in this talk. We have strong evidence already that this second conceptual model might be playing a strong role in the observations that we make, because we see very strong correlations in geochemical proxies. And so I'm going to break this graph down. What you're seeing here is the composition of a variety of mid-ocean ridge basalts and arc front volcanic glasses. On the x-axis, I'm plotting barium over lanthanum. This is a commonly used geochemical proxy for the amount of slab-derived materials beneath a given volcano. And that's just because barium partitions into aqueous fluids, slab-derived aqueous fluids, preferentially relative to lanthanum. So that means that as you see an increase in barium, it's an indication that you've added more and more slab-derived materials into the subarc mantle source for a given volcano. So that's the x-axis. And then the y-axis is, again, this parameter oxygen fugacity, this time expressed relative to the QFM buffer instead of NNO. The same general rule applies, where more oxidizing conditions plot towards higher values of this delta QFM value. And so when we look at this, we see this really striking correlation between oxidized volcanic materials and increases in the amount of slab-derived material present in their mantle source. And so this is a really strong clue that this second conceptual model is playing a role. So this has been a really exciting step forward in understanding these kinds of problems, but there's still something that we don't quite understand, which is what this causal link is. How exactly are these slab-derived materials oxidizing the overlying mantle wedge? What is the oxidizing agent in this scenario? And so what I want to talk about and what I hope to convince you of during this talk is that sulfur might be the causal link. So why, out of all the elements in the periodic table, are we focusing on sulfur? Turns out that sulfur is an incredibly interesting element, an important element in the context of these types of questions, because sulfur is present in two different valence states in silicate melts. So at more reducing conditions, sulfur is present dominantly as sulfide or S2-. And in more oxidizing conditions, sulfur is present dominantly as S6+ or sulfate. And so what's probably most interesting about this plot, this is a calibration, an experimental calibration of how sulfur valence states varies with oxygen fugacity on the x-axis. And what's most interesting is actually this transition region, this narrow transition region from about QFM0 to QFM+2, where sulfur is present in some proportion of both of these two chemical species. And so what gets especially interesting is when we overlay what we know about different types of volcanics against this plot. So we know that Morb has an oxygen fugacity of somewhere around QFM. So that plots around 0 on this plot. And as you can see, this means that most of the sulfur in mid-ocean ridge basalts is present as S2- or sulfide. But what's really interesting about volcanic arcs is that if we overlay information about the oxygen fugacity of basaltic arc magmas against this plot, we see that it straddles this transition almost completely. And this is incredibly interesting because it means kind of two things. One, it means that sulfur is incredibly responsive to changes in the oxidation state of a magma. But you can also flip that on its head and think about what happens to a magma if we start adding oxidized sulfate into a magma that was previously dominated by this sulfide or S2- chemical species. And so we can explore this by doing a very, very simplified calculation. So all I'm doing in this calculation is titrating molecules of S6+ or sulfate into a basaltic melt with around 1,000 ppm of sulfide. So this is kind of a Morb-like melt based on what we know. And so as I start to titrate more and more moles of S6+ into this melt, there are two things that happen. One is that the sulfur content of the melt goes up, which is unsurprising as we're titrating more and more sulfate into the melt. But the other thing that's really crucial to thinking about this is that the oxygen fugacity of the melt also starts to go up as we're adding this oxidized species of sulfur into it and it's reacting with all of the other melt components. And so again, this is an extremely simplified calculation, mostly used as a proof of concept or an illustration of the processes that I'm interested about. But what's interesting is that even this really simplified calculation broadly mirrors the observations that we see at ARCs. So I'm plotting here estimates for the sulfur content and oxygen fugacity of basaltic arc magmas, and we can see that this very simplified calculation is actually able to reproduce these ranges fairly well. And so these kinds of processes are why we're so interested in sulfur as a key player in these types of processes. And so to narrow in on the specific question that I'm interested in, I really want to understand whether or not oxidized sulfate from the subducting slab can influence the oxidation state of the mantle wedge and the magmas that form there. So does slab dry sulfur explain the elevated oxidation state that we see in volcanic arcs? And so to investigate this question, we used Lassen volcanic area as a natural case study. So Lassen volcanic area is located in the southern tip of the Cascadia volcanic arc. This is a great location to do this work for a few different reasons. One big one being that the Cascade Arc is known as a global end member for the thermal regime. It's a very warm subduction zone. And what I mean by that is that the crust subducting underneath the Cascades is very young and hot relative to other subduction zones. And so this is a great point of comparison to arcs like the Mariana Arc, where similar work has been done in the past. Another reason why Lassen works so well for this purpose is that there's a very rich history of kind of petrologic investigations in this area. And we can take advantage of that because what we're trying to do here is kind of ambitious. We want to integrate information about sulfur mass transfer and sulfur valence state and mantle melting and arrive at a kind of cohesive framework for thinking of all these things together. This is the conceptual model that we're going to be working within. This is based a lot on a previous work by Christina Wolowski in Lassen volcanic area. She was able to use a variety of constraints, including isotope ratios of volcanic eruptive products and trace element proxies to make a really strong case for this conceptual model. So what you're seeing here is the downgoing subducting plate. We have the upper and lower oceanic crust, and we also have this thin hydrated portion of the lithospheric mantle in that downgoing plate that was created by outboard faulting. And so when this subducting plate reaches subarc depths, that thin hydrated lithospheric portion dehydrates and releases aqueous fluids into the overlying altered oceanic crust. And importantly, it's actually melts of this altered oceanic crust. So these are silicic aqueous or silicic water-rich melts that rise up into the mantle wedge and participate in mantle melting. So this is the framework that we're going to be working within and layering in information about sulfur and about magma oxidation state. So I've broken this down into a couple of different steps so we can think about breaking this problem down into kind of discrete stages. So step one in all this is just about characterization. We want to find a way to characterize the sulfur content and the oxidation state of Lassen magmas. And so to do this, we're going to use olivine-hosted melt inclusions. So melt inclusions are one of the best ways to understand the volatile content of magmatic systems. They form at depth when a growing crystal starts to grow and form a small inclusion around it at depth. And then as that magma parcel erupts, including that crystal, in this case, olivine crystal, acts as a tiny pressure vessel around that melt inclusion. And so once that inclusion quenches to a glass, all of the volatile elements that would normally degas during eruptions, so things like sulfur, chlorine, water, remain entrapped in that melt inclusion. And so although they have their complications, they're one of the best tools to directly measure volatile elements in a magmatic system. You can think of them as kind of magmatic fossils. The catch is that these melt inclusions are very small. The scale bar is about 100 microns, or about the width of a human hair. And so a lot of the creativity in melt inclusion work comes from trying to extract as much information as we can from these very small samples. So that's the type of sample that we're going to be working with, and we're specifically going to target small basaltic cinder cones for this work. So this is a very simplified conceptual cartoon showing the difference between volcanic cinder cones and larger stratovolcanoes. So these are the more classic volcanoes that you might think of, things like Mount St. Helens. And the reason why we're targeting cinder cones in this case is that they tend to have simpler magmatic plumbing systems, whereas stratovolcanoes often have a very complex network of magma storage bodies beneath them. Because they're active for so long, these cinder cones are very small, kind of short-lived features. In the past, people have considered them to be monogenetic, kind of a direct drinking straw to the mantle. As we learn more and more, we know that they're often have their own storage systems, but that they are still far simpler than larger stratovolcanoes. So that's why we're targeting this type of volcanism for this study. Okay, so what do these cinder cones look like in the field? This is a really classic example of a cinder cone in Lassen volcanic area. It's actually called cinder cone. It erupted relatively recently, so it's very well preserved. You can actually hike up it in about 40 minutes. So if you're ever in this part of the world, highly encourage you to check it out. But I wanted to put this image on here because it really shows how simple these volcanic systems are. These are essentially a big pile of volcanic tephra with a few lava flows next to it. And so again, because we're trying to think more carefully about kind of mantle processes, slab drive material processes, these work really well for us to minimize the influence of crustal differentiation in our volcanic record. So to do this study, we targeted 6 different cinder cones in Lassen volcanic area. What you're seeing here is a digital elevation map of the region. So Lassen Peak is kind of the main volcanic edifice in the center. And I apologize if it's hard to see, but all of these gray crosses are actually mafic vents that have been previously sampled. So again, what you're seeing here is a really rich history of petrologic investigations in this study. And the colored symbols represent cinder cones that we specifically targeted for this project. And so we hiked out into the field and we collected volcanic tephra from each of these cinder cones. It turns out that this tephra works really well as a substrate for construction and road development. And so a lot of these cinder cones have been previously quarried, leaving these really incredible outcrops and exposures that turn out to be really handy for sampling. So we hiked out to 6 of these cinder cones, we collected volcanic tephra, and we selected olivine-hosted melt inclusions from tephra of each of those different cinder cones. And so what I'm showing here is sulfur concentrations in those melt inclusions from those 6 different cinder cones. So each box here and each symbol type represents one different cinder cone. So Borg, BBL, these are all different cinder cones. In this plot, each symbol represents one analyzed melt inclusion from that cinder cone. And the gray shaded region represents the concentrations of sulfur in mid-ocean ridge basalts for comparison. So again, using mid-ocean ridge basalts or MORB as kind of our test case. On the x-axis is the forsterite content of the olivine host, which gives us information about the conditions during entrapment of these melt inclusions. And even in this very simple plot, just showing how much sulfur each of these melt inclusions has in different cinder cones, we start to see that there are some clear differences. So we have cinder cones like BBL that have sulfur concentrations that are pretty indistinguishable from MORB. And in contrast, we have cinder cones like BRM that show clear elevations in sulfur concentrations with respect to MORB. And so because we know that we're in a subduction zone and in a volcanic arc, one of the best questions you can ask is whether or not slab-derived materials are driving the differences that we're seeing. And so to think about this a little bit more directly and start to make kind of more quantitative comparisons between each of these cinder cones, we're going to use this melt inclusion data to calculate primary magma compositions. So you can think of these as kind of fresh, uncrystallized mantle melts that are entering the crust prior to any modification. And because we targeted fairly primitive early crystallized melt inclusions for this study, we're able to use a relatively simple reverse olivine crystallization model to calculate these things. So what you're seeing in gray is that reverse olivine crystallization model, backtracking until we get to a composition that's roughly in equilibrium with the mantle source. And so the most important thing to keep in mind here is that these large symbols represent primary magmas beneath each cinder cone, but in all cases, they're calculated directly based on individual melt inclusion data. And so for the remainder of this talk, these large symbols will represent primary magmas for each melt inclusion, but again, always underlain by this large melt inclusion data set. Okay, so now we can get into kind of processes and mechanics of how things might operate. So we want to know whether or not variations in sulfur content at Lassen are being driven by the influence of slab-derived materials. So things released from the downgoing plate into the overlying mantle wedge and the mantle source for each of these cinder cones. And so what I'm plotting here is two geochemical proxies that help us investigate this. On the x-axis is strontium over neodymium. So this proxy is very similar to barium over lanthanum, just slightly different to be more sensitive to the influence of slab-derived melts. And any increases in strontium relative to neodymium is an indication that there's more and more slab-derived material present in the mantle source for a given volcano. The y-axis sulfur dysprosium was created with a similar logic in mind. So any increases in sulfur relative to dysprosium can be an indication that you've added more and more sulfur into the mantle source for a given cinder cone. And so when we make this comparison, we see that there's this correlation between dysprosium and strontium over neodymium values, which is incredibly helpful because it's a clear indicator that sulfur in these magmas is partially derived from this convecting slab. In other words, it is differences in the amount of slab-derived material that's driving these variations in sulfur content that we're seeing. And what's really promising about this data set is that the behavior of sulfur is very consistent with what we see in other volatile elements that we know come from the slab. So elements like water and chlorine. And in all three of these elements, we see this strong correlation between the volatile element and our proxy for slab-derived material. So when we look at all this information together, we start arriving at a very clear picture of a water-rich, chlorine-rich, sulfur-rich, slab-derived material variably influencing all of these different cinder cones at Lassen. Okay, so this leads us to step 2. What does this slab-derived sulfur look like? We've characterized the sulfur contents of Lassen magmas, we've tied it to slab-derived materials, and now we're trying to figure out where exactly the sulfur might be coming from and what it might look like geochemically. And so to do this, we're going to use sulfur isotopes. So I'm showing here a basic histogram of the abundance of different isotopes of sulfur on our planet. You can see that the vast majority of sulfur is present as sulfur 32, but that there's a small portion of that's also, small portion of sulfur that's also present as sulfur 34. And so we're going to use the ratio of this sulfur 34 to sulfur 32 to think about how that parameter might be used as a tracer for sulfur behavior and for the source of sulfur. And so when we do this work, we're going to use this delta 34S notation. And this is just a means to express the ratio of sulfur 34 to sulfur 32 in reference to some agreed upon standard. So that's all this proxy is indicating. Okay, so why are we interested in using sulfur isotopes as a tracer? What I'm showing here is a compilation of estimates for all of the different sulfur isotope reservoirs that we might expect to see in a subduction zone. You can see that overall it's quite complex, but we can actually simplify it down into 2 key reservoirs. So the first reservoir that's really important to understanding this question is the source for mid-ocean ridge basalts, which is the depleted mantle. There's some disagreement about the precise value, but we all agree that newly formed altered oceanic crust and the subarc and the mantle that forms that crust has a value of somewhere around 0 per mil, so delta 34S of 0 per mil. And so the second reservoir that's really important is the isotopic composition of seawater. So seawater dominantly has sulfur present as sulfate, and we know that the isotopic composition of that sulfate is somewhere around 21 per mil. And so what's really important about these 2 reservoirs is that that newly formed oceanic crust interacts with the seawater sulfate in 2 areas before it subducts beneath volcanic arcs. So seawater interacts with newly formed oceanic crust at hydrothermal systems near the mid-ocean ridge basalt axis. And we have strong evidence for this of seawater altering pre-existing sulfides within the newly formed oceanic crust and also depositing seawater derived anhydrate. What we're also beginning to learn is that there's a second opportunity for seawater to interact with the downgoing plate prior to subduction, and that is during the process of outboard slab bending and faulting. This process allows seawater sulfate to penetrate actually down past the oceanic crust and into that thin layer of lithospheric mantle. And so what we're really interested in trying to figure out when we look at sulfur isotopes in arc volcanoes is whether or not we can see the signature of the seawater sulfate and the eruptive products. So in the past, one complication to considering these questions has been that sulfur isotopes can be heavily modified by the process of degassing. And so we really wanted to understand how we could characterize sulfur isotopes prior to this process. And so to do that, we used SIMS to directly measure the sulfur isotopes in our olivine hosted melt inclusions. So these melt inclusions were trapped prior to sulfur degassing. And so we're able to characterize sulfur isotopes of arc magmas that are unmodified by the process of degassing. And we'll record mantle signatures a little bit more directly. So we conducted our analyses. These were some of the first analyses of sulfur isotopes in melt inclusions from volcanic arcs, and we took them over to Woods Hole to do this work. And what I'm showing here is the results of those analyses. Again, these larger samples represent averages based on a variety of melt inclusion data for each different cinder cone. And in this plot, we're plotting strontium neodymium, our slab proxy again, but this time we're comparing it to delta 34S. And again, the signature that we might expect to see from the influence of seawater sulfate is to drive these delta 34S values higher towards that 21 per mil end member. And again, for comparison, I'm plotting mid-ocean ridge basalts at kind of our baseline scenario in that gray density contour. And so these results were really exciting because we were able to see a clear correlation between slab-derived materials and increases in this delta 34S parameter. This is really exciting for two reasons. One, it allows us to think a little bit more directly about the mass balance of sulfur from the subducting slab, the mantle wedge, and the volcanic arcs. But it's also really exciting because it allows us, again, to start thinking about what the sulfur might, quote unquote, look like. And we were able to use a variety of constraints that I'm happy to talk about in more detail to establish that these elevated delta 34S values could only have been created by slab-derived materials that contained dominantly the oxidized form of sulfur, so S6+. And so what's really exciting about these results is that we're starting to fill in this conceptual framework. So we know that the slab-derived materials that are being released into the mantle wedge beneath Lassen are isotopically heavy, have high delta 34S values, and that they're very likely to be oxidized in the form of sulfate-rich slab-derived melts. Okay, so this is really exciting so far. We've been able to get really strong evidence that Lassen volcanic area is being strongly influenced by oxidized sulfate-rich slab-derived melts. And so now we want to tackle kind of this big question, which is whether or not this slab-derived sulfate can create the oxidizing conditions that we see in arc magmas at the surface. And so to look at this more carefully, we brought our melt inclusions to one more round of analyses. And this time we're using ZANES. ZANES stands for X-ray absorption near edge structure. It's a type of spectroscopy that's very sensitive to differences in the valence state of redox sensitive elements like sulfur and iron. And so it's an extremely powerful technique for trying to understand these types of questions. So we took our samples over to Argonne National Lab in Chicago to the Advanced Photon Source. What you're seeing here is the setup inside the facility that we use to analyze our melt inclusions. So we have these very high intensity X-rays coming through the ion chamber that go through a series of focusing mirrors, hit our sample, and then fluoresce, and that fluorescence is picked up by the detector. Interestingly, in the case of sulfur zanes, we have to be really careful about atmospheric contamination. And so we actually use this very high-tech helium bag, which is essentially a giant Ziploc, to make sure that our analyses are clean and aren't interfered with. So that's what the setup looks like. And the challenge in trying to do this work is that we need very high intensity X-rays to tease out this really fine structure related to valence state in the glass. But we're also faced with the challenge that these are arc melt inclusions, so they contain substantial amount of water, and so they're kind of unstable and unhappy at the surface. And so a lot of the methods development was trying to find ways to use these high intensity X-rays to get the data we needed without damaging the sample and creating analytical artifacts. So once we worked through that and we got a great data set of sulfur and iron zanes or sulfur and iron valence state for our melt inclusions, we're able to create plots like this. So what you're seeing here is the oxygen fugacity of each cinder cone. Again, this is calculated directly from our iron zanes data, so directly from iron valence state. We compare it to the strontium neodymium parameter, and we again see this really striking correlation. So this is really exciting. We're seeing this correlation between increases in magma oxygen fugacity and increases in the amount of slab-derived material present. And this mirrors very closely the trend that we see in our sulfur zanes analyses. So increasing amounts of slab-derived material is directly linked to increases in the valence state of sulfur. And so when we look at these two data sets together, we're seeing really strong evidence that slab-derived sulfur is directly correlated with increases in arc magma oxidation state. So this is an incredibly exciting observation and shows that sulfur may really be the oxidizing agent that we're interested in. However, we're still kind of stuck at a point here because even though we're seeing these incredibly exciting correlations, we still haven't directly established the causal link. So we need to test whether or not the slab-derived sulfate can actually generate the increases in arc magma oxidation state that we're seeing at the surface. And so to do this, we developed a mantle melting model, and we're trying to simulate this process shown conceptually in this schematic figure. So we want to know if we have this slab-derived melt, this hydrous, chlorine-rich, sulfur-rich slab-derived melt that rises into the mantle wedge and starts to react with mantle prototype and participate in mantle melting, what happens to that slab-derived sulfate? Does it generate oxidizing magmas? Is it diluted by the mantle that it reacts with? And can we track this quantitatively? And so to do this, we assembled a model that tracks both major elements, trace elements, sulfur and iron speciation, and sulfur isotopes. So we're able to directly compare this to our melt inclusion data set as a way to ground our model. And what you're seeing here is the model outputs for a given run, starting from conditions near the slab surface, grading all the way up into the upper portions of the mantle wedge. And we're going to take one model step, which is the peak mantle wedge temperature, as our output to directly compare to what we see at the surface. And so I'll go through quickly what we see under the hood before moving into results. To calculate major elements and to set up the mass balance constraints, we're using P-MELTS models. So what I'm showing here is the P-MELTS model runs for each of our models. Each gray line that you're seeing represents one model run. Again, going from 2.1 GPa into 1.2 GPa. Each green dot in this plot represents the peak mantle wedge temperature that we're using to compare directly to the compositional data at each cinder cone. And what's important about this plot to note is that we're running a series of model runs, grading from low proportions of slab melt to high proportions of slab melt in the mantle wedge. So we're simulating variations in the influence of slab-derived material. And so low proportions of slab melts are shown in lighter colors, and high proportions of slab melts are shown in the darker colors. Let's combine this with what we want to learn about the oxidation state of blast magmas. We're combining this model with sulfur ion redox equilibria calculations. And these calculations have some uncertainty associated with them. And so we made sure that they were grounded in our iron and sulfur Zanes data directly. Okay, so that's a quick peek of what's under the hood, and now we'll move into a subset of our results. So the first thing that we wanted to understand was what this model looked like in kind of our quote unquote best guess inputs. So again, because we're using mid-ocean ridge basalts, it's kind of our baseline, we selected parameters that were solid estimates for the Morb source mantle, for a subarc mantle prior to any modification. So that's that first two values here. So we're assuming that we have a very kind of typical mantle composition, and that into that very typical mantle composition, we're adding sulfate-rich slab melt. The concentration of sulfur in that sulfate-rich slab melt is based on some experimental data that's available. So this is kind of our best guess based on external constraints. And if we compare our model runs to our observed values, we can see that we do see increases in arc magma oxidation state associated with increases in slab-derived material, but that they clearly underpredict magma oxidation state, both in terms of this delta QFM value or this oxygen value, and in terms of this sulfur valence state value. It clearly underpredicts both of these two sets. So although this model seems to be predicting some of the behavior we expect, clearly we're missing something. And so one step we took was to say, okay, maybe what we're missing is that we don't have a good enough handle on the sulfur content of slab melt. So what happens if we ramp the sulfate content in these slab melts all the way to 10,000 ppm, which is about 1 weight%? So if we increase the amount of sulfate in our slab-derived melts, we can reproduce the oxidation state of Lassen magmas a little bit better. So those blue curves match a little bit better with the observed values. But then if you look in the lower right panel, we are clearly over predicting sulfur dispersing values a lot because we're adding so much sulfur into the mantle source. So we might be a little bit on the right track, but clearly we're still missing something important. And so the last scenario that we wanted to test is what would happen if, in addition to increasing the amount of sulfur in our slab melt, we also assume that the mantle source is sulfide saturated. And so if the mantle is sulfide saturated, it will cap the amount of sulfur that's dissolved into slab melts. And this is a pretty reasonable assumption to test because there's evidence from things like calcophile element systematics that many arc magmas are sulfide saturated in their mantle source. So if we make this assumption that a lot of the sulfur in the mantle wedge is hosted in these sulfide phases, we're able to reproduce the observed data really well. So we're able to reproduce both magma oxidation state and sulfur dispersing values really well with this model. And so this model is really useful because it's a really nice proof of concept that yes, slab-derived sulfate can oxidize the mantle source at arc magmas. And so we're able to bring all of this information together to arrive at a really cohesive conceptual model for sulfur recycling at Lassen and how it's tied to increases in arc magma oxidation state. And so this is an incredible step forward, directly linking the mass transfer of sulfur to increases in arc magma oxidation state and being able to ground that in quantitative models. But I would argue that the observations that we make at Lassen and the lessons learned about this kind of southern Cascadia region can be applied to thinking about subduction zones globally. And so there's two reasons for that. One is that one of the really striking outcomes of this work is that the oxygen fugacity values, so again, this delta QFM parameter and the cascade arc that we measure are very similar to the values measured at the Mariana arc. And so this is really striking because both of these two volcanic arcs are in very different subduction zone settings. Cascadia arc is a volcanic arc and a continental arc, a warm global end member. In contrast, the Mariana arc is an oceanic arc, and it's a cold global end member. So in these two very different subduction zones, we see very similar values of oxygen fugacity. this suggests that there's some kind of shared mechanism across different subduction zones globally. We can make a similar comparison with sulfur isotopes. This is a comparison of sulfur isotopes measured in last and melt inclusions in that red bar, the mid-ocean ridge basalts, that gray line, plotted against sulfur isotopes measured in a variety of different reservoirs at volcanic arcs. So this includes high temperature volcanic gases, degas volcanic rocks, intrusive rocks, and seawater sulfate, just for comparison here. And so again, what's really striking here is that against all of these different sample types, so gases, degassed rocks, intrusive rocks, we see that they all share a fairly similar range of sulfur isotope values. And so again, this suggests a shared mechanism of sulfur transfer across subduction zones globally. And so I will leave this as a teaser that if you're interested in learning more about what the global implications might be of sulfur cycling and its relationship to arc magma oxidation state, we recently published a paper that's a compilation of 24 different arc segment melt inclusion compositions. And we start to make some quantitative conclusions about how sulfur cycling might be tied to arc magma oxidation state. So I'll leave that as a teaser, and I encourage anyone who's interested to check out that paper. So with that, I will wrap up. Thank you again for your time, and I'm happy to take any questions.
Okay, thank you very much, Michelle. Now it's time for questions from our participants. So feel free to raise your hand or open your mic to ask a question. And before you ask a question, could you let us know your name or institution? And meanwhile, if you'd like to type, you could also ask a question in the chat, and I will ask a question on your behalf. So go ahead.
Can you hear me?
Okay. I'll wait a bit. Okay, I think somebody else is going to ask questions.
Yeah, sure. Go ahead.
Oh, okay. Okay. I thought somebody else was going to ask a question. Hi, Michelle. Great talk. My name is Huizhang Li. I have a small question about your model. The third graph showing the increasing that QFM with increasing sulfur in melt. Mm-hmm. And it shows that it's increasing curve, but it kind of flattens out at higher sulfur content. Can you explain what caused that?
Yeah, I can go to this plot that has the same model on it. Yeah, it's one of the interesting outcomes of this work. So essentially, when you first start adding sulfate into a dominantly sulfide dominated melt, it has a lot of essentially leverage to oxidize iron and create changes in arc magma oxygen fugacity. As you continue to increase how much sulfate you're adding into the mantle melt, that kind of leverage decreases. So you have a smaller change in ferric iron content for a given addition of sulfate, and that creates that leveling off behavior. So it's kind of a decrease in leverage or efficacy for a given mole of sulfate added. One of the interesting outcomes, it's something that we see in this very simplified titration, but it's also something that we see in the more complex kind of P-melt space model. And I've actually been thinking a little bit about it because it seems to mirror observations that are made in natural samples. So for example, in this Mariana arc data set, we see a very similar leveling off. And so I wondered if those two observations are related.
Yeah, that's quite interesting. Sorry, I'm still not quite clear about I understand that it is for calculating the QFM, you actually that's actually based on the iron oxidation state, right? So it's sulfur 6 plus is going to be reduced to sulfur 2 plus, sulfur 2 minus, and the iron 2 plus is oxidized to iron 3 plus. So are you, because I can't imagine how the calculation went, but is that possible that the iron and the sulfur reaction reach kind of equilibrium?
Yeah.
Is that why there's a leveling off?
Yeah.
Of curve?
Sorry, could you say that again?
So I'm still trying to think. Because we have a few weight percent iron in the melt, and so I can see the maximum sulfur you added is a few thousand ppm. I can only imagine that the sulfur will always be reduced, and sorry, my mind is is going fast. I don't know where it's going.
Yeah. No, I think I understand what you're asking. Let me see if I can explain it a little bit better. So the calculation is based on this equilibrium. You're correct that we're not calculating oxygen fugacity directly based on sulfur. What we're doing is using this equilibrium relationship. So this is, representing an equilibrium constant at a given temperature. And we're recalculating this equilibrium relationship for every kind of parcel or mole of S6 plus that we add in.
I see. Now I understand.
Yeah. Okay, good.
Sorry. Just to double check with you. So I guess there's at some point all the sulfur will be in an oxidized form, will be sulfur 6 plus.
Yeah, exactly. So I guess one way to think about it is that, this relationship is nonlinear. And so exactly, as you add more and more sulfate, you get to the point where almost all of the sulfur is present as sulfate anyway. So adding in additional sulfate doesn't have a strong effect.
Yeah, now I understand. Thanks very much. Okay, I have another question. I will try to say it clearly this time. Like you mentioned the difference between the Larsen magma and the Mariana arc. One is warm subduction, the other one is cold subduction. And I'm just wondering for your model, because I know it's maybe the oxygen fugacity allies for two different kinds of magmas can be similar, but we know that the chemistry can be quite different. For example, the barium-lattice ratio or strontium over neodymium ratio can be quite different between cold subduction and warm subduction. I'm just wondering if your model can reproduce the chemical data for example, Mariana arc.
I haven't tried it just because all the trace element behaviors tuned for slab melting scenarios, whereas the dominant model for the Mariana arc has some addition of slab dry fluids. So I don't know if the model would reproduce the barium lanthanum ratios. But you could make some broad comparisons around oxygen fugacity as a function of sulfur content, and those broad comparisons as I think about it, broadly match, but I'd have to tweak the model a little bit to make it applicable to Mariana arc.
Okay, I just remember I have another small question. It is about the percentage of slab melt you add to the mantle. And if I remember correctly, some of the percentages can be quite high. What's the consequence of that high percentage of slab melt addition? Because it may change the composition of the magma produced from mantle melting.
Yeah. So there is a broad range. You're thinking of these values when it gets up to 30% out here?
Yes, that's right.
Yeah, some of them do get quite high. One thing that happens, so the 30% value is for the slab melt to mantle peridotite ratio near the slab mantle interface. And so that actually gets diluted a little bit as it rises. And so by the time you get to the peak mantle wedge temperature that we're taking to represent the outputs, that'll decrease a little bit, so it won't be quite as extreme. That being said, you know, some of these higher, you know, cinder like BRM, they do have fairly high proportions of slab melt on them. It might be that there's a little bit of uncertainty there related to the subarc mantle prior to subduction modification. So, you know, doing like a, you know, precisely quantifying how much slab melt is beneath each cinder cone to like percent values would probably require that individual model runs are created for each cinder cone based on variations about what we know in the subarc mantle source at Lassen. I'm not sure if it answers your question. Yeah.
Yeah. So in your model, did you get the results for major elements?
Yep.
Okay. It's kind of interesting. They don't change that much. That's interesting. Okay, I'll read your paper more carefully after this. Thanks very much. Great work.
Yeah, feel free to get in touch.
Thank you. Thank you.
Okay, next question is in the chat. It's a little bit long. I'm going to read it, but feel free, everyone, to read the question in the chat. So first question is the difference of the oxygen fugacity between the arc volcanoes and the MORB, which they with a higher oxygen fugacity volcanoes. However, for the FO sulfur content, only some of them have higher sulfur contents than the MORB. So Jin Wang is asking what is the explanation for that?
Yeah, that's a great question. Let me see if I have a good slide for that in here. Okay, well, I'll just go back to the one you're talking about. Right, so basically, there are a couple different things happening here. One, the most, so it's not that surprising that a lot of these cinder cones have very small elevations in sulfur content with respect to MORB. And that's because the relationship between the sulfur solubility of arc magmas as a function of oxygen fugacity is strongly nonlinear. I wish I had a slide showing it, but it broadly mirrors this relationship, which is also nonlinear as a function of oxygen fugacity. And so what that means is that, you know, as you start to increase oxygen fugacity relative to MORB, when you first start increasing it, the response in sulfur solubility is fairly small if you're in this kind of near delta QFM0 region. But as you get into more and more oxidizing conditions, there's an exponential increase in the sulfur solubility. And so that's why a lot of the more reduced cinder cones, even though they're slightly more oxidizing than MORB, don't have a large increase in how much sulfur they can hold. And that, again, that's like another point of evidence for a sulfide saturated mantle melting source, that we see these direct relationships between the sulfur content of slab-derived material and, the sulfur content of olivine hosted melt inclusions and what we think the oxidation state of the mantle source was for them.
Okay.
There was a separate second one.
Okay, the second question is that since you propose the sulfate is an oxidizing agent, so why this sulfate or oxidizing agent that rarely occurs in exhumed slabs in the orogenic belt?
Yeah, you know, it's a question that I'm curious about too. When I've talked to people about it, it's not clear how much anhydrate sticks around in exhumed slabs just because it's so water soluble. So there's a question of, you know, would you expect to see it in the field record, even if it was there at depth? Also note that, you know, a lot of these reactions in the slab don't necessarily need to have like anhydrate veins in them in order to generate sulfate-rich slab fluids. So for example, if there's enough ferric iron in the slab that during dehydration reactions, the sulfur that's released is oxidizing, that's another way to get to the elevated sulfur isotope values that we see because of sulfur isotope fractionation at the slab surface. So when you think about these things in detail, you may not actually need, you know, substantial like anhydrate veins in the slab in order to generate sulfate-rich slab materials. But I am eager to keep learning more from that field as they start to look into the sulfur question more.
Okay, I have a quick following question before I think someone else should ask a question. So for example, for this slide, the horizontal axis, as far as I know, was from the experimental petrology work that people with the gas mixing furnace control oxygen capacity, and the vertical axis was what the people measured before. But for the natural samples, both for your work, I think for Mary Brown's work, you also calculate oxygen capacity. So how was that? Oxygen capacity was calculated.
Yeah. So the oxygen fugacity in both of those two data sets were calculated using iron Zanes data, and then using Crescent-Carmichael to convert ratios. Crescent-Carmichael 1991, which is a parameterization of this to calculate oxygen fugacity based on that iron valence state data.
Okay, but in Crescent, Carmichael, they didn't consider sulfur in their case, and your situation that a lot of sulfur are involved.
Yeah, no, that's a question we've asked. There's not really any experimental evidence for or against, you know, Crescent-Carmichael's applicability to sulfur-bearing systems. But broadly, we know that Crescent-Carmichael works well and is consistent with experimental data when using natural samples. So there's no clear evidence to suggest that Crescent-Carmichael isn't appropriate for sulfur. For example, when we use constraints from things like back-arc glasses, mid-ocean ridge basalt glasses, which are all sulfur-bearing, and compare it to experimental constraints, which often don't have sulfur, they converge at really similar conclusions and results. So there's no clear evidence that, you know, Crescent-Carmichael isn't applicable to sulfur-bearing systems, but it would definitely be great to investigate that directly.
Okay, next question, please.
Hello, I have a question.
Yeah, go ahead.
Can you hear me? Yeah, I'm from Institute of Geochemistry, Chinese Academy of Sciences. Thanks for your great talks. Michelle, I have a question about that's another paper by Peter Tolan, and that paper said arc magma is oxidized by water dissociation and hydrogen incorporation in oxopyrus. Could you give us some comments on that paper, because it's totally different opinion about the arc magma oxidation state?
Yeah, I think I know the paper you're referring to. It's a really interesting mechanism. When I've sat down and thought about how that mechanism might scale to an entire mantle wedge, it's not quite clear to me that the mass balance works out. So how much water you'd need to drive a given amount of oxidation versus how much water you see in arcs. So I haven't seen clear evidence that that's borne out by field relationships, but it's an interesting mechanism. and one that maybe, can be tested more in detail in the future.
Okay, thank you.
Okay, any more questions? Okay, thank you very much again, Michelle, for your talk, and everyone, please open your video before we turn the meeting off to show your appreciation for our speaker today. So Michelle, could you stop sharing your screen so that you could see more faces of our participants who attended your talk? Okay, everyone, please, if you can, please open your video. We are going to keep this on for about 30 seconds before we turn the meeting off. Okay, thank you.